Now we're going to talk about kinetic molecular theory. This is the simplest model for understanding the behavior of gases. And in this model, we think about a gas as being a collection of particles. Those could be molecules or atoms. And those particles are in constant motion. So this illustration here, we've got these little particles and they're zinging around, right? And here, this one ran into the wall. There's this little explosion thing here. It bounced, it came off. And here, these two ran into each other and they bounced off of each other. So they're a lot like ping pong balls, just, flying through the air, and they hit something and they bounce off. Have you guys at least heard of that ancient video game Pong? The original video game, right? And you had this paddle at the bottom and there's this little blip that moved on the screen, right? And it would bounce off the walls and you had to move your paddle to keep it from falling into the void at the bottom of the screen. So gas particles behave like that Pong blip. They will keep traveling in a straight line at a constant speed until they run into something. And then they bounce off. They don't lose any energy when they bounce off. It's called an elastic collision. So they'll bounce off and they'll just keep going on. So this gas container here is like a Pong game that's just, all self-contained. There's no paddle at the bottom and there's a whole bunch of Pong blips and they're just going around. Yeah.
So since you said they don't gain any energy, do they gain any?
They don't lose any energy.
Do they gain energy?
No, they don't. So they don't gain or lose energy. And that's something that's really different about gas molecules. That's, because regular objects, a ball flying through the air, it's got the force of gravity pulling it down, and it's got wind resistance or friction from the air that it's flying through. These particles don't have any wind resistance, air resistance, because they are the air, right? They are literally flying through nothing. So they'll collide with each other, but then they bounce off of each other, just like, ping pong balls or billiard balls, except those are not exactly elastic, and these are. So they do not lose energy running into each other. So they're just bouncing around. So that's the basic idea for kinetic molecular theory. So the size of the particle is small enough that we can just ignore the size of the particle. So here what we're doing is we're assuming that particles occupy no volume at all, even though they have mass. Of course they have volume, but the volume of them is so insignificant compared to the entire volume that it just doesn't matter. So as an example, if you have argon gas at STP, the actual atoms occupy 0.01% of the gas volume. And if those argon atoms were the size of a golf ball, the closest neighbor would be 4 feet away. There's lots and lots of empty space. So another way to think about this is we can think about people. Okay, so if you think about people getting into an elevator, right? And you've got like maybe 10 people in a small elevator. Does the size of the people matter? If they're like kindergartners or, linebackers from the football team, right? You got some really big guys in there, and 10 might be a really tight squeeze, right? But the 10 kindergartners would fit just fine. That's what solids and liquids are like, where the particles, the people are touchingly close, and so the size of them matters. The gas is more like the state of Wyoming. So I remember taking a trip with my kids a long time ago, and you look at the AAA guidebooks, and I realized the population of the state of Wyoming is about the same as Fresno without Clovis.
Without Clovis?
Without Clovis, the entire state has the same number of people as Fresno. It's not a small state. So there's just lots and lots and lots of space, right? So unlike the elevator, where everybody's really close and the size matters, does it matter how big the people are there? No, there's way more than enough space. So that's kind of how gases are. Any question?
I was just gonna ask you how big is my room, but it don't matter.
Yeah, I'd say it's probably about an average size state. I mean, California is a little disproportionate, but it's about that big. It takes a significant amount of time to drive through. Okay, so that's one idea about gases. So the average kinetic energy of the gas particles is directly proportional to their temperature. So kinetic energy is the mass of the particle times its velocity squared divided by 2, right? So when you increase the temperature of the gas, the particles move faster. Their mass stays the same, but their velocity will increase. So one thing that's important to understand is in a sample of gas, even though they're all at the same temperature, not all the gas particles are moving at the same speed. The average speed increases with temperature. You have some that are kind of slow and some that are really fast. The average kinetic energy is related to the temperature. Another important thing about gas particles is that when they collide with each other or with other things, that is an elastic collision, meaning they do not lose any energy. So if you think about, let's see if I can do this. No, that's not. No. So if you think about these two balls, see if these are billiard balls and they're rolling towards each other and they hit each other, what happens? They bounce off, right? Well, what if instead of billiard balls, you had lumps of clay, balls of clay? They're, kind of soft and squishy. And you manage to roll those across the floor and they run into each other. Are they going to bounce off of each other? No, they're just going to kind of go boom and stop. That is an inelastic collision. Their kinetic energy gets lost to heat energy when they collide. Billiard balls are closer to elastic collisions. Gas particles actually are elastic. They bump into things and they don't lose any energy. So the total kinetic energy of the colliding bodies remains the same. I guess I got ahead of myself. There's the picture of the clay, right? Now, it does not mean that this ball or this gas particle has the same speed that it did before. One could be slower, but then the other one will be faster. But the total amount of kinetic energy is the same. But here, kinetic energy gets lost to heat. So gas particles can just bounce around in a container and they don't need any extra source of energy to keep them moving. They'll just keep moving. So these ideas in the kinetic molecular theory explain some of the things we've learned about gases. So gas pressure. Where does gas pressure come from? Well, those gas particles are constantly moving and they strike the container with a force. It's a really small force because they're really, really tiny. But you've got a lot of them and they're striking the container frequently. And so that combines and gives us a constant pressure. So the pressure from a gas is because all those little particles are hitting the walls. Any questions about that? I kind of think of this as being like pecked to death by a duck. Heard that expression? A duck comes up and bites you, right? You're like, ow, that's not going to kill you, right? But if you've got 1,000 ducks and they just keep pecking at you, right, it's going to become a problem after a while. So an individual gas particle running into the container has very little effect. But when you have millions and gazillions of them doing that over and over and over again, it leads to pressure. Boyle's law talks about how the volume of a gas is inversely proportional to its pressure. So if we make the volume smaller, decrease the volume, forcing the molecules into a smaller space, those particles are still running around at the same average kinetic energy. We're going to have more of them collide with the container at any given time because the container is smaller. So that means the pressure is going to be higher. Charles' law, volume is proportional to absolute temperature. So when we increase the temperature of the gas, the average speed, and therefore the average kinetic energy increases. So if we're going to keep a constant pressure in that container, we must have to allow a larger volume so that those increased collisions spreading out over a larger surface area would maintain the same pressure. So that's Charles' law. Avogadro's law, volume of a gas is directly proportional to the number of gas molecules. So if we put more gas molecules into the container, we're going to have more collisions with the walls, right? So here we're trying to keep the pressure constant. If we want the pressure to be constant, then we'd have to increase the volume of the container. Any questions? Dalton's law, the sum of the partial pressures gives us the total pressure of the gas mixture. So the gas particles are negligible in size. They do not interact with each other. They just bounce off of each other. Particles of different masses are going to have the same average kinetic energy. Because the average kinetic energy is the same, then the total pressure is the same, even though the particles are of different sizes. So it really depends only on the number of particles and not on how much they weigh. Kinetic molecular theory implies the ideal gas law. If you're interested in that, the derivation is in the textbook. Importantly, the theory predicts behavior that is consistent with our observations and measurements of gases. And just a reminder, scientific theory is the most powerful kind of scientific knowledge. You know, in everyday life we say, well, that's just a theory, that's just your crazy idea. But in science, a theory is a very significant thing. This is a model for how gases work. Now, is this model perfect all the time? No, this model breaks down under certain conditions. But even that can be useful because when we look at those places where the model doesn't work, that can help us to understand even more about gases. So we've been talking a lot about kinetic energy of gas molecules. So kinetic energy, Ke, can be defined as 1/2 the mass times the velocity squared. If the gas particles have different masses, like you have a mixture of gases, then the only way that they can have the same kinetic energy is if they have different velocities, right? A larger particle would be traveling at a lower velocity, a smaller particle at a higher velocity to have the same kinetic energy. So when we look at a gas mixture at a given temperature, lighter particles travel faster and heavier ones travel more slowly. And so this kind of, my kids played football, so I've spent a lot of time watching high school football games. So you think about the maybe the center, right, on the O-line, and he's a big guy, right? When he runs, does he run really fast? No. Well, I mean, it's not that they're not fast. I mean, some of those guys are fast, but compare him to the running back. Yeah, the running back is going to be much faster, but he's probably going to be significantly smaller also, right? Because it's really hard for a big person to run very quickly, But those two people have roughly the same kinetic energy as they're moving. The smaller guy's moving faster, the bigger guy's moving slower, but he's bigger, right? So that's kind of how the gas particles go. When we talk about average velocity, we're talking about a funny kind of average velocity called the root mean square velocity. It's really similar in value to the average velocity, but it's what we use when we talk about gases, so just be okay with it, please. So that has this symbol U, RMS, root mean square. Not sure why it's a U, but it is. So the root mean square velocity of a collection of gases is proportional to the square root of the temperature and inversely proportional to the molar mass, the square root of the molar mass of the particles. So here we have an equation. The velocity is equal to the square root of 3 times r times the temperature divided by the molar mass. Now, in this equation, we're going to use a value of the ideal gas constant that has different units. This is not liter atmospheres per mole Kelvin, this is joules per mole Kelvin. So it's 8.314 instead. And then in order to make the units work out, we need to have the molar mass in kilograms per mole. This is an equation that you might need to use on an exam, but I'll give it to you. I don't expect you to remember that one. You should be able to remember, though, that the faster particles are at a same energy are going to be lighter, and the slower particles are going to be heavier. So this is a graph showing a variation of velocity distribution with molar mass, right? What the heck are they talking about? So on the x-axis here, we have molecular velocity, the speed at which these particles are moving. And on the y-axis, we're graphing the relative number of particles that have that velocity. So if we look at oxygen, we see that oxygen, a lot of those particles are going to have molecular velocities down here in the 300, 400 range. And as you go to higher and higher, the number of them having that velocity drops off. And by the time you get out to about 1200, there's very few oxygen molecules that are going to have a velocity higher than that. So oxygen has a molar mass of 32. And then over here we have hydrogen molecules, molar mass of 2, so significantly smaller, right? So here, the average velocity is more out here in the 1500 to 2000 range. These particles are moving faster on average, but there are some that are moving very slow and some that are moving even more quickly. So what this is telling us is that the larger particles are going to have a lower velocity, but it's also going to be more compact, more close together. The velocities are going to be close together. As you get smaller and smaller particles, lighter particles, their speed is going to increase, but the distribution is also going to increase. So there's a lot of variation in the velocity of the small particles compared to those of the heavier particles. If we look at a particular gas sample and change the temperature, we also find a difference in the distribution. So here, this is nitrogen gas. And again, we've got molecular velocity here and relative number of molecules here. So at 273 Kelvin, the distribution is pretty narrow. Most of the molecules are in this range in terms of their speeds. As we increase the temperature, that distribution broadens out and there's a lot more variation. We've got some particles moving very quickly and some moving very slowly. So this question is asking us to calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So we need that equation. Oops. So we're trying to calculate the root mean square velocity, and that's going to be 3RT divided by M and the square root of that. So to calculate that, we need the ideal gas constant with the correct units, we need the temperature, and we need the molar mass. So the temperature is 25 degrees Celsius. But all gas calculations with temperature have to be in kelvins. So we need to convert that to kelvins. So we get 298 Kelvin. R, for these problems, is blanking. I want to say there's an 8 in there, but I don't think there is. Yeah, it's 8.314. Okay. Guess what? I'll give you that one too. 8.314 joules per mole Kelvin. And then we need the molar mass. So this is xenon. Look at xenon in the periodic table. We have 131.3 grams per mole. This value needs to be in kilograms per mole because a joule is a kilogram meter squared per second squared. So here, where we've got joules, that's kilograms per meter squared second squared. And if we want the gram here to cancel out with the mass in there, they both have to be in kilograms. So we can convert this to kilograms, 0.1313 kilograms per mole. So the root mean square velocity, we've got 3 times the temperature, 298 Kelvin. I'm sorry, R comes first. 8.314 joules per mole Kelvin times 298 Kelvin divided by 0.1313 kilograms per mole, and the square root of the whole thing. Let's cancel out the units that we can. So kilograms, kelvins are going to cancel kelvins, and moles are going to cancel moles. So let's do the math here. I've got the square root of 3 times 8.314 times 298 divided by 0.1313. $237.93, and then the units are going to be it's the square root of joules divided by kilograms. Those are the units that didn't cancel out. A joule is a kilogram meters squared per second squared. And if we divide that by a kilogram, the kilograms cancel out, and we end up with meters squared per second squared. So this part in here is equal to that. The square root of meters squared per second squared is meters per second. So this is going to be 238 meters per second. I do not expect you to remember the units that are hiding away in the unit joule. I'm showing you this just to show you why that has to be in kilograms. And so you can say, well, yeah, I remember she showed us this thing and it looked like the units worked out, so it's good enough, right? Yeah. Sometimes you just don't really need to know all the little details all the time. Any questions? Yeah. The M?
Yeah.
So they use M here as a variable for molar mass.
Oh, okay.
Yeah. We've got altogether too many M's going on, right? Sometimes it's mega, and sometimes it's mass, and milli, and it's like all over the place. So, any other questions? Yeah.
So since like numerically our answer doesn't change, just the units are changing. When we get to the joules and kilograms, can we just like draw an arrow and write the number with the meters?
Okay. So what you can do is write this out with the units that come with all of these things, and then do the math. So you get the number 238, and wave your magic wand, meters per second. Yeah. Units are important, but understanding how these units work out is not really worth your time. Yeah, honestly. Now, milliliters to liter conversions, some of you are still having trouble with that. That's important. Okay, this, And these types of calculations are going to show up on this exam, the exam for this chapter, and there might be like one question on the final exam, but it's probably not going to use the equation. It's probably going to be more conceptual about, which particle is going to be moving faster based on their mass. So again, if you're struggling with stoichiometry, I give you permission to just kind of skip this and keep struggling with stoichiometry because it's more important, okay? (238 meters per second). So here's a conceptual question. And this is something we should be able to think about. This doesn't involve solving complicated equations. This is, do we understand how gases are? So this is saying, which sample of an ideal gas has the greatest pressure? Assume that the mass of each particle is proportional to its size, and that they're all at the same temperature. So if these particles are shown as bigger, does that mean they're heavier than the little tiny particles? Yeah, it says assume the mass is proportional to the size. So this particle is going to weigh more than this little particle. But they're asking which is going to have the greatest pressure? C. Yep. The pressure of a gas depends on how many particles there are, not how big they are. Right? So these have higher mass, but they're all at the same temperature, so these big guys, like the O-line football players are really big, they're going to move more slowly. Same temperature, same kinetic energy. These guys, like the running backs, they're smaller and faster, but they have the same energy. So these two, with the same number of particles, would have the same pressure. Doesn't matter that these are big particles. This one has more particles, and so the pressure is going to be higher. Any questions? That's a lot more important than root mean square velocity.